Okay, great. Welcome to the second block of the tutorial on privacy-preserving natural language processing. And in this part, we're going to be talking about some formal guarantees. And in particular, we're going to be talking about differential privacy, which is a go-to framework for privacy preservation in machine learning and NLP in particular. So let's set up the field of differential privacy with some terminology, because it might be kind of confusing for new starters. So we have somebody who is a trusted curator, and we have a data set. So the trusted curator holds a database or a data set, where basically a data set is a table, and each entry in this table is linked to a single person. And at the same time, each person basically in the data set has only a single entry. So which means we have basically a table like here, and the rows are persons, and they are completely independent, and they can have sort of a tabular format, some attributes or text, or could be completely any objects, so to say. So formally, we have this data set here, which is a table. We call it a small x. We just n individuals, and we can basically say it's an n tuple, sort of. But we also use many different notations, so we can see data set as a capital D or a capital X and so on. But here in this notation, x1 corresponds basically to Elise, the first entry, x2 is Pop, and so on. So this shouldn't be any surprise. We have a notion of neighboring data sets. So the definition of neighboring data sets is that data set X and data set X prime differ in one row. And this difference of two data sets can have two variants, basically. In the first variant, X and X prime have the same size, basically, and we just swap, basically, one person. In the second variant, the data set X prime, the neighboring, is bigger by one person. So one person is removed or added to the data set. And these two options will not protect the same thing later on. So the first variant will basically care for protecting the value of this record, while adding or removing one person from the neighboring data set will protect also whether this person is in the record or not. So basically the presence of the record in there. And let's have a look at, because it's a central topic to differential privacy, this is where the differential comes from. So let's have a look at two data sets and why they are different. So neighboring, excuse me. So we have data set X here, which consists of three persons, Elise, Bob, and Charlie, and they have these attributes here. And for example, now by removing one person, so removing Elise, we would end up with a neighboring data set X prime. So they differ by one row by removing one person from this. So this is the second variant we spoke about. But also, we can have two data sets where we just replace one person. And here, we're showing a data set of size 1. So we have basically just one row of a table, and we replace this entry in the table and end up with different data set, basically. Even though it looks a bit extreme, it does follow the definition, and it will be useful for the so-called local differential privacy. So the data set could be of size 1, and if we replace one entry in the data set, we end up with a neighboring data set. And this is a central concept in differential privacy for many reasons. So then let's move on, because we have data set and we're going to do something with the data set. For example, do some queries or apply some function on this data set. So we, as in the terminology of differential privacy, we are an analyst, or at the same time, we are the bad guy. We are the adversary as well. So we want basically to get some information about data set X. So for example, we want to ask some queries. So query is typically used in the world of differential privacy. And typical queries could be, for example, a counting query, which is how many items are in the data set. It could be a mean query. So for example, what is the mean income from my data set? Or it could be any other numerical query which output a vector of real numbers, for example. But we're not restricted to numerical queries only, because we can have basically any arbitrary query which outputs any object. So it transforms the data set X to any objects we want to have. So let's have a look at some examples of numerical queries. So we have this data set here again, like just 3 items and 3 persons, basically. So as I said, like counting query could be, how many persons are there? So we have 3 persons. Mean query could be, what is the mean income here? So the mean would be roughly well, 60,000 and something. So there's a typo here. But this is more interesting, like general numerical query. So maybe we're asking for a histogram of word count. So this is something where we come a little bit to NLP now. And we want to take all these texts, all these Facebook posts, and just get a histogram of words. So building vocabulary and their frequencies. So this is also a numerical query where we, want to output this dictionary sort of. Or even like a very arbitrary query could be just give me a copy of Facebook posts. So basically one-to-one function where we just output this column verbatim. Why not? This could be an interesting query as well. And for us, for NLP people, this is basically start working with the actual data with the text. So yeah, why not? But there's more examples of the queries. So for instance, how about, yes, so return Facebook post. This is what we have. And how about this one? So let's use the income as the predicted variable, y. Let's use the Facebook text of this entry as an input to a neural network for income prediction, okay? Let's run a forward pass and the propagation on this and return the gradient. So it's gonna give us a interesting numerical query. So basically the query is giving us the gradient, and it also is a query. And as we will see later, this type of query, basically where we want some information from the data, will help us to protect privacy of individuals during training with stochastic gradient descent, basically. So this is also a query. So now we have the data set, we have the query, and we can now formalize basically what is differential privacy or the pure differential privacy. So we as a trusted curator or somebody who owns a database and is the trusted curator needs to randomize the result of the query. So basically the counting query, for example, could be how many persons is in the data set, and if the answer is 3, then we need to add some random value drawn from a certain probability distribution. So this is very important. Differential privacy protects privacy by randomizing the response, randomizing the result of the query, adding some noise. And we call this process a randomized mechanism or algorithm. So in the differential privacy world, a mechanism is a key concept. And we use this letter M, or we also use the M parameterized by the function or the query running on that, or just MX, MFX, and so on. So there's very different, very various, notations for that. So we have this randomization, and what pure differential privacy guarantees is that, well, we have this epsilon here, and this epsilon has a name. It's called the privacy budget for a reason, which I will explain later. Why is it budget? But it's some non-zero, more than zero real constant, maybe 1/10 or 1 or 2 or 3 and so on. And then the pure differential privacy guarantees that for every pair of neighboring data sets, X and X prime, so we know what the neighboring data sets are already, right? They differ by one person, and therefore anything this mechanism outputs, so any of the output of the query, of the query F, we have this bound of probability. So the probability of observing this output given one data set over the probability of observing this same output given the neighboring data set is bounded by this epsilon constant, by this privacy budget. So this is the formal guarantees. So let's have a closer look at it. So we also say pure differential privacy is epsilon 0, and the 0 corresponds to a different letter, which we will explain later on, but the pure differential privacy is epsilon 0 differential privacy. So here again, we have the definition. Basically, privately querying a data set X, where with LEs, so this is one of the examples of the data sets, we have LEs in there, and data set X prime, where there is no LEs in there, so this neighboring data set, it will give me 2 results, right? So maybe the counting query will be different. Probabilities of these 2 results must be similar up to these factor A to epsilon. And you might be asking, like, why are these probabilities here? Well, because there's randomness. So the mechanism is a random process. We're adding some noise, and we can reason about the probabilities in this process. So this was the definition of pure differential privacy. We have neighboring data sets, we have different queries, and we know that there is some bound on the probability of revealing some information about each person in data sets in terms of probabilities. So let's have a look at some basic differential private mechanisms. So we start with maybe the easiest mechanism for numeric queries. So this is the Laplace mechanism. And just recall that the Laplace distribution, or the probability distribution function of Laplace, is parameterized by mu, by the location, and by b, which is the scale, so the size of the noise. And here's the definition. So when we want to privatize a query output by adding noise from Laplace distribution, what do we need to know? I mean, we basically draw it from zero location distribution, but we have to know the scale b, because basically the amount of noise is determined by the scale of this Laplace distribution, and we have to determine that to basically protect differential privacy and to be aligned with the definition. So for this, we need to understand the so-called L1 sensitivity, or global L1 sensitivity, which we describe as delta F. And L1 sensitivity tells us what is the maximum absolute value, or L1, or Manhattan distance difference, of the query, and for any two neighboring data sets, right? So we have to know the maximum impact which one person will have on the output of our query, right? So we try to reason about all the possible neighboring data sets, and then we just take the maximum difference when two neighboring data sets are put through the function. It goes like the maximum impact or maximum difference on the query. So for example, if you had a counting query, you might be thinking, what will be the sensitivity of the counting query? What happens if you remove one person and just then ask how many persons are in the data set, right? So the result, the sensitivity of counting query will be 1, because the function can change by maximum 1 because you remove one person from the data set, right? And then the scale of the Laplace noise is then proportional to the sensitivity, which we just determined, for example, for this counting query, and to the privacy budget epsilon we want to spend. So the privacy budget epsilon is something we design, like a hyperparameter or a constant. We just say our mechanism will be such and such private. And then it works as basically running the query as we want, and then adding the random noise, which is drawn from the Laplace distribution, scale at 0, and then we just determine the scale, centered at 0, and we just determine the scale, which is proportional to the epsilon and to the delta. We can visualize this Laplace mechanism. And for example, here we have two Laplace distributions with two means. So basically, we would have maybe a counting query, and this would be like the drawn for x, and this would be drawn for x prime. And now the definition of pure differential privacy tells us that anything which will be outputted, so for example here, this number when it comes here, so the ratio of these two will be bounded by the a to epsilon. So no matter which outputs comes, I can only tell it comes from the second or the first one. The probability I can tell this is from x or x prime, the probability is bounded. So this is the formal guarantee, no matter what comes out. And if you want to have a look at a formal proof, I put it on my blog here, so we can just read it through the mathematics, and that really that it holds for the Laplace mechanism. Another popular one for pure differential privacy is the exponential mechanism, and it's used for, let's say, for discrete outputs. So let's have some arbitrary range, or it's a set. So something which we want to output from our mechanism. The exponential mechanism is defined into some also utility function, which takes basically a data set and maps each data set and the output range to some utility scores. So for example, here we're coming a little bit closer to NLP use. So where X is a word and the range, the R, is another set of words, the utility U could be, for example, some similarity of word X and all the words in the range R. For example, the similarity of word embedding. And we want the utility to be, the higher utility is better, so we would need to map, for example, the embeddings to not being close enough with 0, but maybe just inverse, for example. And then the mechanism, when we want to privatize the data point X, would look into, draw a random element from this range. And obviously, the distribution we're drawing from will be determined by the utility. So we want that the mechanism output some element from this range with the maximum possible utility score. So basically, we have like this distribution maybe over words, which will be some maybe long tail. And obviously, we want the closest word or the most similar words in this case to be drawn, and we would maybe pick this one as an output of the query, basically a replacement of the word. And this exponential mechanism is also a pure epsilon zero differential private, where we need, again, to make it really formal, we need to find the utility score, or the sensitivity, the sensitivity of the utility score. The utility score we know already. It's the mapping from database and a data point and the range, but we need to determine the sensitivity. And this is, again, over all neighboring data sets. I think that here's a typo. This should be X prime, So we're running all through possible neighboring data sets and all outputs from the range, and just want to determine what's the maximum impact of any individual being removed or added to the database or change in the database in any circumstances of outputting any output. What is the maximum? Because this will kind of limit the noise we have to add. So then, having determined the sensitivity, this exponential mechanism selects and outputs an element from R as desired, and the probability is proportional to this formula. So basically, we would kind of draw from a probability distribution, and this would be proportional to this formula. And again, if you're interested in the proof, you can have a look at this kind of step-by-step blog post. So we talked about pure differential privacy, where no matter what comes out, we already have this feeling that. Not a feeling, we have the guarantee that we bound the probability of finding out whether it's from X or X prime. But maybe we want to make a little bit of relaxation and try something relaxed, which is approximate differential privacy. So let's have a look at a definition of a concept called privacy loss random variable, which might be central in this approximate differential privacy area. So this is the definition of pure differential privacy when we're saying, no matter what you output here, for all the neighboring data sets, we bound all these, we bound the probabilities by this privacy budget. And if you think about it, this fx, it's a random variable basically, because there's some randomness. So we can see it as a random variable, which is parameterized by the query and the data set. And also as a random variable, it has some probability distribution, which is maybe up to us to design. And if we see this as a random variable, this whole function is a function of a random variable, which is, again, a random variable. So we would say here, basically by taking logarithm of this term and getting rid of this exponent, as we have here, we call this the privacy loss random variable, which is parameterized by the mechanism of X, the mechanism of X prime, and the output. And then the definition basically says, well, the privacy loss random variable is bounded by this epsilon. So it's another view. Maybe we can have a look at one example of the privacy loss random variable, how it behaves. So again, I'm repeating here this definition of privacy loss random variable. And here, what we see is that this privacy loss random variable is always bounded from above by this epsilon, by the privacy budget. Well, if you think of bounds of random variables, we typically think of tail bounds, like, well, what is the tail bound of Gaussian distribution, for example, or such queries. Here, we're saying that the privacy loss random variable, which we just simply describe as L, is always smaller than epsilon, always, with probability 1. I mean, this will be always bounded. Later on, we'll extend this notion by some relaxation, but now in pure differential privacy, we're saying the privacy loss random variable is always bounded by epsilon. And what does it mean? Here's an example distribution of the privacy loss random variable for a counting query, and I used here a Laplace mechanism of epsilon 2. So this is the x-axis, is the epsilons. And we're saying that this distribution is kind of weird distribution because we're putting it through a certain complicated function, but we see that it doesn't go higher than the epsilon, which is desired, right? So we can't have anything exceeding the epsilon with this as defined here, basically. This is great, but this is very strict, and we maybe want to relax it. So here again, this is the pure differential privacy, so this always holds. But we can add some relaxation with they call it cryptographically small delta. So typically 10 to minus 6, 10 to minus 7, or there's some, it's a hyperparameter, which we again need to choose, but it's a really small number. And here we're leaving the strictness of always and saying, well, the privacy loss random variable is bounded from above by epsilon, but like 99 something 90%. Or if we just rewrite it, the probability of exceeding the privacy budget is exactly delta. And if you think about it, well, okay, we're now actually, the privacy loss random variable now, it can have tails beyond epsilon, but these tails must remain very small, right? So we had the previous example, we had this very weird kind of distribution, but it was cut by epsilon 2. Now we're saying, yeah, maybe the loss can get a little bit over 2, but this whole probability will be very small, this delta. So we're allowing some relaxation here, which will be useful later on. And let's have a look at a famous and widely used mechanism for epsilon delta approximate differential privacy. And it's the Gaussian mechanism. And now, if you remember, we had this L1 sensitivity for the Laplace mechanism, and now we're moving into Euclidean distance. So we're defining global sensitivity or L2 global sensitivity using basically Euclidean norm and not the Manhattan distance. And now the Gaussian mechanism works as any other mechanism. So we have the original query, and then we're adding some noise. The only difference now is that the noise is not drawn from a Laplace distribution, but it's drawn from a Gaussian distribution. And the Gaussian distribution is, again, zero-centered. And then it's parameterized by basically the scale, sigma square here. And now there's actually two versions of the Gaussian mechanism. And the original, so to say, one is, which the proof you can find in the appendix of this algorithmic foundation of differential privacy. And this one works actually only for epsilon smaller than 1. So this is really important to keep in mind. But then basically you can determine the scale of the noise to have certain properties, and you can find the proof why it is so. But it's important really to keep in mind that it only holds for small epsilons. However, you might want to use bigger epsilons, and the epsilon choice is a different story, how to design the epsilon and what it really means. Maybe even for people in the database. But let's say you want to have epsilons greater than 1. Why not? So for that, I would suggest to look at this NLP Gaussian mechanism, which works basically for any epsilon. And again, it works like that. We have the the original query, and we're adding noise, which is drawn again from a Gaussian. So far so good, nothing has changed. But how we determine the standard deviation or the variance is much more complicated than in the previous one with like simple formula. Now there's the formula is much more complicated, and typically it's computed numerically using the error function of the Gaussian. And for that, I would really recommend this paper by Bjorn Bale, excuse me, where you can also see the algorithm. And basically, this helps us to having epsilons, in the range of 0 to almost infinite, I would say. Okay, so now we have we know pure differential privacy. We have the relaxation of epsilon delta differential privacy, and two mechanisms like the Laplace and the Gaussian mechanism. What is also important for us, and we're now coming closer to NLP, so to say, it's important that the privacy budget as a meaning as a budget, because we can be eating that up for the whole sort of analysis of the data. And for that, we need something which is called a composition, because we can compose a couple of algorithms, or we can basically run several privacy algorithms or mechanisms after each other, and the result will be also private. So if we're running several mechanisms on the same data, for example, we have the composition theorems. So yeah, well, basically we can be running the same or various privacy mechanisms on the same data. So there are several variants, but basically the basic composition tells us that the epsilons and deltas, they add up. And that's why it's called budget. So you have the budget for the whole several analyses. And if you have k steps, and it's composition of k mechanisms, and each of them is epsilon delta differential private, you just multiply them by the number of steps you're taking. So it's going to be k epsilon, k delta differential private. This is the basic composition. Well, there is more, because this is kind of strict and not necessarily, well, what you're actually trying to achieve is to have as low epsilon and low delta as possible, because it gives you less noise and it gives you better, let's say, accuracy down the road. So the k-fold adaptive composition of an epsilon delta mechanism, the goal is to use smaller overall budget, which is what we want. And here is basically the formula, which is looks a little bit complicated, but at the end of the day, it gives you a mechanism which is basically eating up something which is smaller than just the basic composition. And this will be helpful. Why, if you think about it, when do we need to run analysis of the same data over and over? Well, for example, if we train a machine learning model or using stochastic gradient descent, where we just iterate over data set multiple times, and yeah, if you iterate over multiple times, this would be maybe not optimal, but adaptive composition or advanced composition is something which is better, because we don't have to add so much noise and which would destroy basically the whole model. Now we're moving from the theory, which is really important to understand, all the concepts, to some applications of differential privacy in NLP. And we are just scratching the surface here, but I believe it's a nice trade-off between the pure theory and the applications. So the first thing we are really interested in is that we want to publish models trained with differential privacy. So imagine you're training a model, for example, fine-tuning, and on some sensitive data set, and you want to publish that. So it's possible, not easy, but possible, to extract training data from the models. There's very cool research papers on that. So we want to prevent that and use differential privacy maybe instead. So let's have a look at let's say the hammer nowadays for training differential private model, which is the stochastic gradient descent. So our setup is that we have a, for example, labeled IID example. So what is IID again? Independently, identically distributed examples. Exactly. For example, tabular data. Yeah, right. So we have these. Each example is a single person. This is what we have. And in this paper from Martin Abadi and other people, when they proposed this algorithm, they use privacy content, which kind of utilizes composition of the mechanisms we're talking right now about. And this algorithm, this accountant, computes the privacy cost at each access to the training data. So when we're training with stochastic gradient, we're compute gradients over time and multiple times over maybe the same data. And this privacy accountant takes each step and kind of remembers what was the budget eaten here and accumulates costs as the training progresses. And the trick here, this paper is very heavy actually, and there's very many clever tricks in there how to make it, how to eat up as little noise as possible or as little budget, privacy budget as possible, and to make it differential private. So they used proposed numerical integration to get bounds on the moment generating function of the privacy loss random variable for all the moments up to 32. So well, the privacy loss random variable, we can see it as a as a random variable, and each random variable has a moment generating function where you take the expectations of the variable power k, basically, or no, excuse me. So there's a formula for that. I'm sorry for that. But basically, you can use this these bounds based on Markov inequality to find tighter bounds and so on. So it's a little bit like black magic, but if you follow the procedure, you end up with a proper privacy guarantees. But for us, it's important the easiness actually of this algorithm in the training. So here's the stochastic gradient descent now with differential privacy, and the only difference between, we might be aware of mini-batch stochastic gradient descent. So the difference here is that we're using something which we call lot. So it's a set of examples, and we also determine the number of steps in advance. It's not like, well, we might have actually, we don't need it, I guess, but let's take it for granted. We have number of steps. And then in any stochastic gradient descent, we're running through each steps, and then in each step, we sample the training data into the lot. So basically, for each training example, we decide with probability size of the lot over number of all examples, and it's uniform distribution of the training examples, basically. And we decide whether we take this example to the lot or not. So we're basically sampling, I would say, a batch, but we call it a lot. And so we sample examples for the lot, and it will be different samples in every run of that. This is important, this sampling. And then, well, there is no magic here and later on, because for each example in the lot, we compute a gradient for this example. So this is like in standard SGD. We're gonna clip the gradient per example. So this is something very special to DP-SGD, and there will be some consequences of that. So we're basically saying, let's take a L2 norm of this gradient for this example and clip it by some constant, because we need to bound the function in order to be able to add some noise, which is not infinite. Then, for each of these examples in the lot, we're adding the Gaussian noise, as we saw before. How do we determine the sigma square? It's a different story. So this is this moments accountant, for example. But then having added the noise, we have for each example in this lot, we have a gradient, which is noisified. And then we just estimate the gradient of the lot by averaging. So basically, it's the same as in mini-batch stochastic gradient descent, where we take the average, which gives us some good estimate of the gradient at a point. And we update the parameters and end up with better parameters for the model and repeat the whole thing. So this is great. The only thing which is hard is this clipping gradient per example, because this is very costly and this is very prohibitive because you have to do it for each example independently, and then it's not really so there's frameworks for that, but it's getting slower. So now we have this training algorithm, and how can we apply it in NLP? So basically, DP-SGD is standard treatment of training neural nets with differential privacy. So typically, we would use it for fine-tuning of classifiers. Absolutely, this would be like a go-to framework, and nothing can go wrong here, I guess, because we have IID examples, we have labels, everything is great. The thing is, and we have the persons, like, okay, this is important. We have each person kind of corresponding to one example. This is important notion of differential privacy. This is why it works. How about a pre-training of large language models? Well, it's a different story, because for two reasons. So first one is a technical challenge because of this, which I mentioned before, that per example, clipping is really computationally prohibitive. It's not cheap. So you have to make workarounds and implement the things in JAX or in other frameworks. So it's technically challenging to some extent. And then the other is more kind of what's the objective? So how is, for example, an expert prediction objective compatible with the perspective of persons RIID rows in a table? And to be honest, I don't know the answer to that. I'm certain there's a couple of papers discussing what it means for a language model to be private and how these two interact, but this is something to keep in mind because we talked about the tables and the origins of differential privacy. And if you use the hammer, differential private stochastic gradient descent for different objective, you have to be sure that you know what you're protecting at the end of the day. So another application in NLP of differential privacy could be, basically synthetic data generation with models trained with DP. So here's one example. I think it's on Archive last year that you can take a language model, for example, GPT-2, and use a framework, Opacus, which is one of the implementations of differential privacy in PyTorch, I guess. And you can basically train a generative model or fine-tune on a particular data set. So they took Yelp reviews and generated, conditioned some control codes, for example, what's the review of the score. So you fine-tune your model on your, Yelp are not really private data, but let's pretend they are private data. So you fine-tune your generative model on these training data, and then you can basically generate, by conditioning on something, you can generate synthetic data, which should correspond or which should kind of mimic the distribution of your training data, of your private data, but not revealing anything from there because the privacy guarantees are coming from there. And they used like downstream classification on synthetic data and showed for this epsilon of 4 that the drop in the in the classification accuracy is not that big, right? But let's take it with a grain of salt because it's an archive paper for first, and second, the question is whether Yelp is really private or how much of Yelp is already in pre-trained GPT-2. So I don't know. The authors didn't discuss this detail there. So there's so many tiny tricks in differential privacy which might go wrong. Anyway, another thing my group has been working on is data publishing with local differential privacy, which basically the idea is each individual gives already privatized version of the example. So there's no trusted curator, right? We don't trust anyone. So everybody privatize the data before giving it out. And the idea of privatizing text is just to convert to a latent vector representation using, for example, some encoder-decoder, then adding DP noise in the middle to the example in this latent representation, and then decode back to text. The problem here is that, like, inherent challenge is that this high dimensionality of these internal vectors, the latent vectors, comes with a need for very large noise, and it might typically destroy the utility. And actually here so we have a couple of papers on that, for example, a DP bar for writing, where we're trying to push the latent representation to be still usable, but small as possible. But the epsilon values we're using the budget are super high, and from the privacy perspective, high epsilons are not private anymore. So the question is now open, like whether are meaningful epsilon values achievable for this task at all. So wow, it's we made it. A little bit of theory, mathematics, a little bit of differential privacy, and how can we use it for natural language processing. So let's recap. What are the takeaways here? So the differential privacy provides formal guarantees with exact probability bounds on the privacy laws. So it's really formal, and you have to prove things, and you can disprove things if they are proven wrongly. I think like the takeaway message is like for fully supervised training with DP-SGD, full supervised training with DP-SGD is a go-to option. So it can't go any wrong, I guess. And there's frameworks implementing that like Opacus, TF privacy, and others. The question with pre-training language models or data generation, local DP, word level privacy, and so on. So there are very tricky, but there could be details that just maybe don't fit implicitly the notion of differential privacy we had at the beginning, or use some different relaxations or different notions of privacy. So we have to be always careful that what we're buying is actually what we wanted to buy. Having said that, thanks a lot. I'll be happy to talk to you live at EACL and get some feedback and some discussions and your experience as well. So it's been a pleasure. You'll find all the slides on the GitHub link to our tutorial. So thanks a lot. See you later.